Hello, welcome back. My name is Salma, and in this video I'm going to be talking about strict alternation, or as some people call it, turn variable. As usual, I'm going to start us off by an example, and then I'm going to put the idea behind strict alternation in words. Next, I'll go over the pros and cons for this approach, and finally we'll see the code together. And as always, you can find the detailed timestamps in the caption. Okay, so I'm reusing this example I used for the mutual exclusion video, but don't worry, you don't have to see that video to understand the example. I just thought to reuse it because who doesn't like donuts? This example talks about two processes, process 0 and process 1. I'm not really concerned about the details of what these processes do, so I'm just gonna go ahead and say that process 0 eats donuts and process 1 makes donuts. And they have this shared memory location that carries the total number of donuts. The idea behind strict alternation is that these two processes will take turn to enter their critical section and hence access the shared memory location. So let's say, for example, process 0 gets scheduled first and it eats 2 donuts. The idea of strict alternation is to let process 1 sit and wait for process 0 to finish its critical section. So process 1 cannot interrupt the execution of the critical section of process 0, which includes updating the shared memory location. So now that process 0 is done with its critical section, it's time for process 1 to take turn. And the same thing is going to happen with process 1. It is not going to let process 0 interrupt the execution of its critical section, which is the time it accesses the shared memory location. So process 1 makes 6 donuts and it updates the shared memory location successfully. And this goes on. So process 0 is going to take turn next, and then process 1, and then process 0, and so on. So to summarize, strict alternation is a software solution for the problem of race condition, and its main idea is that while one of the processes or the threads is taking a turn, the other must sit and wait until the first is done so that the second can take its own turn. Now let's take a look at the pros and cons of this approach. So the good thing that this approach fixes the problem of race condition. However, it has multiple cons, one of which is busy waiting. Busy waiting is what happens when a process sits and waits for the other process to take turn. This is due to the nature of strict alternation, which is that two processes or threads must take turn in a strict manner in order to access the shared memory location and be in their critical section. Let's go back to our example to understand this more. The last process that executed its critical section was process 1, which makes donuts. Now let's say that process 0 doesn't get scheduled for some reason. In this case, process 1 will have to sit and wait until process 0 gets scheduled, enters its critical section, and exits its critical section. Only then process 1 can start its own execution. This is what is called busy waiting, and it's very inefficient because as a process is waiting, a lot of CPU cycles are wasted. Another drawback for the strict alternation approach is that it violates one of the main requirements for mutual exclusion. This requirement says that unless a thread or a process is in its critical section, it should not prevent any other thread or process from accessing its critical section. This principle was violated by strict alternation, and it actually caused busy waiting that we were just talking about. In the latest example I just showed you, process 0 prevented process 1 from entering its own critical section, not because process 0 was in its own critical section, but because process 0 had not taken its turn yet, and this caused that process 1 was prevented from entering its critical section. So yes, process 1 was prevented from entering its own critical section, but it wasn't for the reasons stated here. Finally, and mainly because of the two cons we were just talking about, strict alternation approach is not used in practice. Okay, so enough talking about theory and let's look at some code. I have here two coding snippets for process 0 and process 1, and they are really similar, so I'm just going to go over process 0 and then it's going to be the same for process 1. What we have here is a variable of type int, and we called it turn. and this variable holds the number of the process whose turn is next. So for example, if it's process 0's turn, then this variable is going to be equal 0. This variable doesn't have to be called turn, but this is just the convention, and that's probably why they called strict alternation turn variable. Okay, so let's go back here. Here we have a while loop that is always true, and this is to ensure that the code inside the body of the while loop is going to execute over and over until something breaks this loop. Next, we have a very important while loop, and this while loop does not have a body, and this is actually what makes it very important. This while loop keeps checking if turn is not equal to 0, and as long as it's not equal to 0, it keeps looping on nothing. Now remember busy waiting that we were talking about a few minutes ago? This is exactly where it happens. Process 0 is just gonna sit here and wait, and it's not gonna be able to access its critical section until this condition becomes false, meaning that turn becomes equal to 0. Normally what would happen after that is that process 0 is going to execute its critical section and then change turn to be equal to 1 or the number of the other process. But let's think about what would happen if process or thread 1 tries to interrupt the execution of the critical section of process 0. And this is known as race condition. In this case, process 1 is going to try and start execution from here. It's going to check if turn is not equal to 1. And it's not going to be able to continue execution and get to its critical section until it gets out of this while loop when turn is equal to 1. Now turn becomes 1 when process 0 is completely done with its critical section. Only then process 1 can stop looping and enter its own critical section. That's all what I have for strict alternation. I know it can get overwhelming, but don't worry, nothing you cannot learn. Thank you so much for watching. If you have any questions, feel free to contact me. Next video, I'm going to talk about Peterson's solution. Don't forget to like the video and subscribe to the channel.